Hello, everyone. Welcome back to the last part of the chapter 6. Is it chapter 6? The last part of the video that was chapter 7. Okay, so the last part of the chapter 7 for our Chem 65 course, we never quite got to Hess's law of formation reactions. And I was running out of time and I didn't want to rush it. So I'm going to finish it up right now. Okay, so let's see, this slide is heats of formation. Okay, so because energy is a conserved quantity and it's a state function, at least enthalpy is a state function, that means we only need to know the final and initial state of a system. So we can add the energy up like Lego bricks. So if you look at this equation here in white, you have the enthalpy, the standard enthalpy of a reaction is the sum of the standard enthalpy of products minus the sum of the standard enthalpy of reactants. So this idea of the final state minus the initial state, we can do that because enthalpy is a state function. So for example, if we have this equation, silicon tetrachloride in the liquid phase and water in the liquid phase, gives silicon dioxide in the solid phase and HCl in the aqueous phase. So we have a balanced chemical equation and we're asked what's the enthalpy of this reaction. So we want to take the standard enthalpies of formation of the products. So silicon dioxide. So where would you find this information? You'd find it in an appendix in a textbook or online. So I've got 1 mole of silicon dioxide. I look up the enthalpy of formation of silicon dioxide and I find out it's 911 kilojoules per mole. I've got 1 mole of it, so I have 1 multiple of 911 kilojoules. I then add the enthalpy of formation of HCl. So I look it up in a table, it's minus 167 kilojoules per mole. I multiply it by 4 moles because I have 4 in the balanced chemical equation. I subtract from that the enthalpy of formation of the reactants. So silicon tetrachloride is 687 kilojoules per mole, and I've got 1 mole's worth, so I multiply by 1. And then I also have 2 water molecules at 286 kilojoules per mole. I have 2 of them, so I multiply that by 2. And then I add up all those components and I get negative 320 kilojoules. So remember, energy is always positive. If ever you have a negative sign as an output, that just means it exits the system. So the surrounding gets warm and that would be registered as an increase in temperature if you measured the surrounding with a thermometer, for example. Okay, so that's enthalpy of formation. And this is also known as Hess's direct method. So the direct method of Hess's law. We also have another form of Hess's law called the indirect method, and that's exemplified in this example. So here we have an equation. So C6H6 liquid plus 7.5 moles of oxygen gas gives 6 moles of CO2 gas and 3 moles of water liquid. So that's the problem we're trying to solve the energy for. And we're given some help. We're given three clues. We've got 3 reactions, A, B, and C. And where would you find these? Well, typically in an assessment they're just given to you. In the real world, you'd have to go look for suitable reactions that would do what we're going to do with these now. Okay, so what we're going to do, we're going to take these puzzle pieces and we're going to try and arrange them in a way that represents the puzzle that we're trying to solve for. So our roadmap here is, it's shown in white. We're going to take reaction A and reverse it. We're going to take reaction B and multiply it by 6. We're going to take reaction C and multiply it by 3. Why would we do that? Well, let's look at reaction A. We're going to reverse A because I know right now the original A in pink, I've got C6H6 as a product, but I want C6H6 as a reactant. So to make a product reactant, you reverse it. So that's why I'm going to reverse A. So I literally take reaction A and I write it backwards. When I write it backwards, I also change the sign of the enthalpy for that reaction. So initially it was positive 49 kilojoules. If I reverse it, it now becomes negative 49 kilojoules. All right, so that's why we reverse A. Why do we multiply B by 6? Well, if you look at B originally, as a product, B is my only source of CO2 gas. So I want CO2 gas in my final reaction. I want CO2, but I want 6 lots of CO2. And I'm only given 1 lot of CO2, so I need to multiply the whole equation by 6. So everything. I have to multiply everything by 6 to preserve the equality of the reaction. So not only do I multiply all the chemicals by 6, I also multiply the energy by 6. So that's why there's a multiple of 6 in the energy down here. So instead of negative 393.5, it's 6 multiples of that. So it's negative 2361 kilojoules. Finally, I multiply reaction C by 3. Why do I do that? Well, again, I need 3 moles of water as a product. My only source of water is in reaction C. So I need 3 of them. So I multiply the whole thing by 3, including the energy. All right. Now I've processed my puzzle pieces and I've rewritten them in the process form in yellow. Now I add them up, I combine them all together, and I can see that I have things that are common to both sides. So the 6 grams of carbon in the graphite form cancel because they're a reactant in reaction B. They're a product in reaction A, so they cancel. I've got 3 moles of hydrogen gas as a reactant in reaction C, as a product in reaction B, in reaction A, so they cancel also. And the only things that survive are all the ingredients from my balanced chemical equation. Okay. So overall, by adding these pieces in this process form, I reproduce my target equation. So now I know I can just add up all the heats. So I add up negative 49, negative 2361, negative 857.4, and it sums together to give me negative 3267.40. This is called Hess's law, the indirect method, because I'm indirectly taking other ingredients, canceling them, and I'm finally producing indirectly what I want. It was prefaced by the direct method, where I take enthalpies of formation and I directly calculate enthalpy. So whether you use the direct or the indirect method, you can get exactly the same answer, exactly the same. This technique, you will get slightly inferior answers, but sometimes this is all you can do. So this is the bond association method. When would you use this? You use this when this is all you can do. So if you have made a brand new chemical in a research lab and you don't have any equations that you can possibly use, you know, to get your desired product, then you would have to do the following. You literally write out your equation, exposing all the bonds. So for example, I have methane gas, 2 molecules of oxygen to give a carbon dioxide, and 2 molecules of water. So I've exposed all the bonds, and then I follow the following reaction equation. The enthalpy of this process is the sum of the binding of the bond energies of all the reactants minus the sum of the bonding energies of all the products. So I take my reactants. I have 4 carbon-hydrogen bonds. So I've got 4 lots of carbon and hydrogen. I've got 2 lots of oxygen-oxygen bond here. And in my product side, I've now got to subtract 2 carbon-oxygen double bonds. And I've got to subtract 2 lots of water bonds. So each water has 2 OH bonds, and I have 2 waters. So that's 4 OH bonds total. I look at my bond energies. Again, it would be in an appendix in a textbook. So 4 lots of CH. Here's the value of 1 CH. We scale it by 4. Here's the value of 1 oxygen double bond. We scale it by 2. That's all the reactants. Then we subtract all the products. I've got 2 lots of a carbon-oxygen double bond and 4 lots of an oxygen-hydrogen single bond. I add them all together and I get negative 802 kilojoules. If you were to do the same determination using Hess's law, you would get a slightly different value. Hess's law is always a superior method. The reason why bond dissociation energies are always slightly inferior is because we're using generic boilerplate bond energy values. So we're assuming, for example, that the OH bond in water, there's only 1 OH bond. No, the OH bond in an alcohol is going to be slightly different than the OH bond in a different type of chemical. So we're using generic boilerplate values, whereas in reality, it really depends on the specific compound. Hess's law takes into account the specific compound. It's more accurate. Bond dissociation energies take boilerplate average values. Where, to use a clothing analogy, this is off the shelf. It kind of fits you, but it doesn't really fit you that well. Hess's law is tailored clothing. It's made to fit you, and it fits very well. Okay, so on that colorful note, that concludes this chapter. I will post both of these videos for my students. Okay, have a good one.